This video is about finding the eigenvalues and the eigenvectors of square matrix. Now, before we go to we start the solution, let's do two quick reviews. The first one, it's about parallel vectors. Now, if I take any vector, for example, let's take vector 1, 1 and multiply it by, let's say, by 2. So 2 times 1, 1, that gives me the vector 2, 2. Now, a quick drawing, a quick sketching of the vectors. This is the vector 1, 1. And this is the vector 2, 2. And what we notice is that they are parallel. So if you take any vector, you multiply it by scalar, you obtain a vector that is parallel to the original one. If the scalar is positive, the two vectors will be in the same direction. If the scalar is negative, the two vectors will be in opposite direction. The second thing we're going to look at is define eigenvalues and eigenvectors through an example. So let's suppose that A is an n by n matrix, a square matrix. Let's suppose that X is an n by 1 vector. It's a column vector. Good. If you take your A and you multiply it by vector X, you are going to obtain X prime. This X prime here may or may not be parallel to X. When it is parallel to X, we call X an eigenvector. Good. Now let's take some example. Let's take A, our matrix, which is negative 2, 2, 3, negative 1, multiplied by a vector, for example, 1, 1. Now, when you multiply 2 by 1 minus 2, 2 by 1 plus 2, and that's going to give me 0 here. 3 by 1, 3 minus 1, that is going to give me 2. Are these two vectors parallel? No. Let's have a look. The vector, the original vector X is 1, 1. Something like this. 0, 2, it's somewhere here. Clearly, they are not parallel. Let's take another vector. So, same matrix. The vector now, it's going to be negative 1, 1. Let's multiply. Negative 2 by negative 1, 2, 2 plus 2 gives me 4 here. And then 3 by negative 1, negative 3, negative 1, negative 4. Compare this with this. We can write the results. Okay, this is the result of the multiplication. We can write it as negative 4 times, hang on, I made the mistake here, time 1 and minus 1. You see, minus 1. Now hang on again, minus 1 and 1. Let's check, yeah? Minus 4 by minus 1 gives me plus 4, minus 4 by 1 gives me minus. So yeah, again, when I compare the results, which can be written like this, it's a minus 4 multiplied by my original vector. So this vector, and this vector are parallel. Now, when this vector, the original one, and the result are parallel, we call this vector, it's an eigenvector. And the scalar corresponding to this, we call it an eigenvalue. Now, let's go to our question, and we are asked to find the eigenvalues and eigenvectors. Let's define them first. let X be a vector, non-zero vector. We want to find X so that when it is transformed or when it is multiplied by A, it must give me another vector that is parallel to X. So this is the transformation of X that gives me a vector. We have seen this in the examples. And then lambda X, lambda is a scalar. And we have seen that when you multiply a vector by scalar, it gives you another vector. So the result of the transformation or the multiplication, lambda X, is parallel to your vector X. This is what we're looking for. Of course, this equation has got an obvious solution, X equal to 0, but we don't want this. We want something not equal to 0. Now let's rewrite our equation as ax minus lambda x equal to 0. We subtract lambda x from both sides. Now we factor x. Now before we factor x, let's introduce or let's use the identity matrix I, and we know that if we multiply I by x, a vector that is one column, two rows, it will give me my x. So we're going to go here, replace the x by ix. We have not changed anything. Good. Now we have x here and x here, so it can be factored out. Call x. Hang on, what am I doing here? Okay. So it's multiply x equal to 0. Now let's call this matrix B. So our equation becomes bx equal to 0, and this is a homogeneous system of equation. When the constant side is equal to 0, we call it homogeneous system. It has a non-zero solution only when the determinant of b is equal to 0. I repeat, this system of equation that we are trying to solve, it's homogeneous. It has an obvious solution x equal to 0. We don't want this. We want solutions that are not 0. The only way is to have determinant of b equal to 0. Good. What did we say? B is, so B is A minus lambda I. A is matrix negative 2, 2, 3, negative 1 minus lambda A. If you multiply the identity matrix 1, 0, 0, 1 by a constant by scalar lambda, you just go and multiply everything, all the elements of the matrix by lambda. So this is what we get. Subtract the two matrices, negative 2 minus lambda. So you just subtract the elements of this from the elements of this. Corresponding elements, of course. 2 minus 0. 3 minus 0. Negative 1 minus lambda. So it's a 2 by 2 matrix again. Now remember, we want the determinant of B, which is the determinant of negative 2, negative lambda, 3, 2, negative 1, negative lambda, to be 0. Now let's review the determinant of 2 by 2 matrix. The determinant of 2 by 2 matrix, it's A multiply D minus B multiply C. So A multiplied by D, negative 2 negative lambda, times negative 1 negative lambda. So this multiply this, minus this multiply this, minus 2 times 3. I am putting everything explicitly before I simplify so that it can be followed later on. So this, now I expand negative 2 by negative 1. This is a multiplication, of course, plus lambda 2 minus 6. And this, remember, must be equal to 0. Now this is called the characteristic equation. The characteristic equation of A, matrix A. Now let's group lambda square, 2 lambda, 3 lambda, 2 minus 6 minus 4 equal to 0. This is a quadratic equation, easy to solve, easy to factor. Lambda plus 4, lambda minus 1. Let's check lambda 2. 4 lambda minus lambda 3 lambda, and 4 by minus 1 gives me minus 4. Now this is a lambda here, yeah? Let's solve lambda plus 4 equal to 0. That gives me the first solution. Let's call it lambda sub 1 equal negative 4. Lambda minus 1 equal to 0. That gives me the second solution, lambda sub 2 equal to 1. So I finished the calculation of the eigenvalues. Okay, so we found the eigenvalues. Now we go and find the eigenvectors, which are the vectors x. Now this is a 0 vector, yeah? Let's put a small v there. Good. Now let our x, the vector x, has component x1, x2. And then rewrite our equation. So it's A. Now let's put A, the matrix, negative 2, 2, 3, negative 1, minus lambda. Lambda is minus 4 plus 4 times I. All these multiply by x gives me the 0 vector with two components, that's 0, 0. Simplify this and put it here. X is x1, x2. Okay. The other side, 0, 0. Now here, what do we have? Negative 2 plus 4 times 1. 2 plus 4 times 0. 3 plus 4 times 0. Negative 1 plus 4 times 1. Now we can solve, so we are solving this system, yeah? We can solve this system by using the equations or the matrices. I assume maybe some of you haven't done it with matrices, so I'm going to write it as a system of equation and solve it. Multiply this row by this column. Is equal to, so multiply this row by this column, you will get this element 0. And then the second row, 3x1 plus 3x2 equal to 0 again. What we can do is to go here, multiply this equation by half. Multiply by half, it will become x1 plus x2 equal to 0. So you multiply 2 by half, 2 by half, 0 by half. Here unchanged. The next thing we are going to multiply this this equation by 3 and subtract it from here. We are trying to eliminate the x1. So x1 plus x2 equal to 0. And here, this is 3. Let's call this equation, let's call it E1. Let's call this equation E2. So this is 3. So this is E2 minus 3E1. So E2, 3x1 minus 3E1 minus 3x1. It will give you 0x1 plus E2 is 3x2 minus 3x2. That will give you 0x2, and this is equal to 0. Now let's continue solving. Now 0x1 we simplify to 0 and then we just leave one variable. How do we solve this? x2 can be any real number. Yeah, if you multiply 0 by any real number, it will give you 0. So this is the solution for x2. Now go and substitute here. So let's put an arrow so that we know what we are doing. We are using this equation and we substitute x2 by t. And when we solve, x1 is equal negative t. Now our vector, our eigenvector, so let's put it here. Eigenvector x is equal to x1, x2, and it can be written as the real number t. X1 is equal minus t, so minus 1 here and 1 here. Again, t is any real number. So this is the first eigenvector corresponding to the first eigenvalue, lambda 1 equal to minus 4. Now let's go and do the same thing for lambda sub 2, which is equal to 1, and solve the equation a minus lambda I x equal to 0. So again, let x, the vector x, is equal to x1 and x2. So x equal x1 and x2 again. Now a is equal negative 2, 2, 3, negative 1. Lambda lambda is equal to 1 multiplied by I. That gives you I. All this multiplied by x1, x2, and it must be equal to 0. Good. Now we simplify here inside first. Now negative 2, negative minus 1, negative 3. 2 minus 0, 2. 3 minus 0, 3. Minus 1, negative 1 minus 1, negative 2. Now this multiplied by x1, x2 equal to 0. So again, I'm going to solve it by rewriting the system of equation. So multiply this row by this column. That will give me minus 3x1 plus 2x2 equals 0. And then the second row, 3 minus 2, 3x1 minus 2x2 equal to 0. Now it's obvious here that we can eliminate by just adding. So if we add, let's call them E1 and E2. E2, this is E1. Now we rewrite the system of equation. We keep E1 as it is. And now we add we add this equation to this equation. When we add side by side. Yeah, so 0 x1, yeah, minus 3, negative 3 plus 3, 0, 2 minus 2, 0, 0 x2 equals to 0. Again, let's put this equal to 0 and solve 0 x2 equal to 0. And again, x2 can be any real number. You put any real number here, you multiply by 0, it gives you 0. And then we go here. So x2 equal to t. Now this gives me minus 3x1 plus 2x2. x2 I substitute by t. And this equal to 0. When I solve this, it gives me x1 equal 2 over 3 t. So when lambda 2 equal to 1, or when lambda equal to 1, for the second eigenvalue, I get the eigenvector x equal x1 x2, and it's equal to x1 2 over 3, here 1, and we put t here, we multiply there. So this is the second eigenvector corresponding to the lambda, to the eigenvalue 1. Now, as a conclusion, let's put all this together. So for lambda 1 equal to minus 4, or lambda equal to minus 4, we have the eigenvector x1, which is equal to negative tt. When lambda 2 equal to 1, this is the eigenvalue. The eigenvector x2 is equal to 2/3 of t and t. Now remember, t is any real number, and therefore we have got an infinite number of eigenvectors. Now, you remember we started with the equation ax equal lambda x. We solved it, we found the lambda, and we found the x. So let's check that when x equal to x1 and lambda equal lambda 1, the equation is satisfied. So this should be ax1 equal lambda 1 x1. Now lambda 1 ax1, lambda 1 equal negative 4 x1. Now we don't know the answer, so let's put question mark here. Let's start with ax1 and prove that it's equal to this. Hang on, it's negative 2, 2, 3, negative 1, x1. So we are doing ax1, x1 negative t and t. Now let's multiply row by column, negative 2 by negative t plus 2t. That gives me 4t. 3 multiply negative t minus 1, negative 1t. That gives me minus 4t. Here we can put negative 4 as a factor, and we will be left with negative t here and t here. And we have proved that ax1 is equal to negative 4 x1, which means we have satisfied this equation for the eigenvalue negative 4 and the corresponding eigenvector. You can do the same thing for x2 and lambda 2 and come up with the same conclusion that ax2 equal lambda 2, which is equal to 1 x2.